ओम भूर्भुवस्वः तस्य वितुर्वरेण्यं भर्गो देवस्य धीमहि धियो यो नः प्रचोदयात्। हे विश्व के निर्माता, तुम्हारे पापनाशक ज्योतिपुंज से हमारा उद्धार हो और तुम्हारे आलोक स्पर्श से हमारी बुद्धि सदा सही दिशा में संचालित होती रहे। वेलकम बैक टू द अनदर इंटरेस्टिंग लेक्चर ऑफ इलेक्ट्रोमैग्नेटिक वेव्स। Myself Ratnesh Shukla, and today in this lecture we are going to cover another most interesting part of this lecture, that is the general form of the wave equations. Electromagnetic waves are the waves which travels through the space in form of coupled time varying electric and magnetic fields which oscillates at right angle to each other as well as to the direction of the propagation of the wave. I don't know how many people of you guys remember the wave equation. If you don't know the general form of the wave equation, you are not going to get a thrill with it. Guys, if I do this and do that, the outcomes is a wave equation, and that is why I want to let you remember the wave equation. The simplest example of the wave is a string. Suppose there is a string which one is tied at the two ends A and B. There is a tension in the string, capital T. Guys, tension is a force by which the both ends of the strings are being pulled. If you just distort the string in some form in this way, then guys, if you release it, what will happen? You see, string will start a motion up and down in y direction. Let's take a small portion of the string at x from the left side. Y is the height of this one portion at the x and at the time t. Now, what is the wave equation? Wave equation is the equation governing the behavior of the y with respect of x and t. I am just going to blow it in this way so that you can clearly visit it, you can clearly look it. Take this one portion. I have taken this one portion under the region dx here. Suppose this one is dx. Okay, this one portion is under the dx. Now everything comes out from the Newton's laws of motion. That is very interesting for me. Suppose there is a tension in the string capital T at that guy, and here a tension capital T. If a string is perfectly straight, then the both forces will cancel out to each other. But if string is slightly curved, then the both are not going to have cancel to each other. Now suppose at an instant the tension T is making an angle theta with the tangent drawn at the string. Then take the vertical component, that is T sine theta. Similarly, take the vertical component of this one down, that is T sine theta 2. Assume this one is theta 1 and this one is theta 2. The resultant of T sine theta 1 and T sine theta 2 will decide the restoring force by which the string is moving up and down, up and down. So the responsible restoring force for the wave motion can be written in this way. Restoring force equals T sine theta 1 minus T sine theta 2. Now here we are going to make some approximations, guys. Suppose theta measured is very small and it is measured in radian. Then you know from the mathematics, sine theta equals theta minus theta cube over 3 factorial plus theta raised power 5 over 5 factorial and some other corrections. Cos theta equals 1 minus theta square over 2 factorial plus theta raised power 4 over 4 factorials and some other corrections. And tan theta, the ratio of above these two guys, that is theta plus theta by 3 plus theta by 5 and some other corrections. Since theta measured is very small, then forget this one, forget this one and forget this one. Obviously sin theta and tan theta both are going to equal to theta and cos theta is going to just 1. Guys, so in place of sin theta we can write down tan theta. Now place here in place of sin theta 1 tan theta 1 and sin theta 2 tan theta 2. That is, take common t within bracket tan theta 1 minus tan theta 2. Now from the calculus you know very well what is the meaning of tan theta 1 at the point this one to the right. Tan theta 1 means the gradient of the slope or the string at this one point, that is, you can write down in this way dy over dx guys at x plus dx, x plus dx minus dy over dx at x to the left, that is at x. Okay, now what will you do with the situation like this when we have to differentiate the same function of x plus dx and x? Guys, you know from the calculus f of x plus delta x minus fx over delta x, if you apply the limit here delta x tends to 0, you are going to get derivative of this one dy by dx. So similarly from here you can guess what would be the value of f of x plus dx minus fx dx, that is dy by dx into delta x, and if you apply limit delta x tends to 0 means we are going to dx. So dy by dx multiplied by dx. So just apply the same analogy here. The difference of these two guys is going to the derivative of which one is already an derivative, that is d2y over dx square multiplied by dx. And what is this one? This one is the net restoring force by which string is moving up and down or executing the wave motion. Now from the Newton's laws of motion, net force is equal to mass into acceleration. What will be the mass of this one portion? Suppose the mass of the per unit length of the string is mu and the length of this one portion is dx, then the mass of this one tiny portion will be mu into dx. And acceleration is something by which spring is moving up and down in y direction, that is d2y over dt square. Why I have used the partial derivative? Because I want the displacement and the acceleration of the spring at the same time. Dx will cancel out to each other, and further from here and further you can write down this one relation in this way: t times of d2y over dx square equals mu d2y over dt square, or you can write down in this way d2y over dx square equals mu by t d2y over dt square, or you can write down d2y over dx square minus mu by t d2y over dt square. If you see this one relation, this one is the wave equation. Now I am going to write this one in this way: d2y over dx square minus 1 by v square into d2y over dt square equals 0. Here v stands for under root t by mu, that is the speed of the wave in the medium in which it is propagating. Speed of a wave is determined by the tension in the mass of per unit length. So guys, this one is the most famous and the general equation of the wave. Don't forget the general form of the wave equation, that is d2y over dx square minus 1 upon v square into d2y over dt square equals 0, where y is the function of x and t. At any instant, if you want to describe the displacement or the vibration of the columns, you need to know the position and the instant at which we are talking about the wave motion. Thank you.